Hello, welcome back. So today we're going to be talking about Le Chatelier's principle. Firstly, let's state what Le Chatelier's principle is, and then we're going to go into a bit of context, and then we're going to discuss the principle in action. So Le Chatelier's principle states that if a change is imposed on a system at equilibrium, the position of the system will shift in a direction that tends to reduce the change. Basically, to put it in layman's terms that may work for you, if you do something to a system, the system will try and undo it. Uh, and you can use this to predict and manipulate chemical systems. First, now towards before we discuss this principle in action, let's discuss something called the reaction quotient. It's essentially the same thing as Kc, but not at equilibrium. Um, the reaction quotient is written the same way as Kc. It's calculated the same way, and you'll note that if K is equal to Kc, the system is equilibrium. If it's larger than Kc, then there must be a net change of products to reactants, and if it's smaller, the inverse is true, that you must be changing from reactants to products. Now, you can sort of do this intuitively. Now, I described K as uh, P over R. Now, if Q, and since Q is the same thing, so Q equals, I'm not going to write it down, but Q is the same thing. If Q is larger than Kc, then obviously if we decrease the numerator here and increase, you'll get a smaller number. However, what is also true is that if you increase this denominator here, you get a smaller number. So there must be a net change of products to reactants, because that way you get a smaller number and you will get to Kc. The opposite is true. If Q is much smaller than K, this must go down and this must go up. Now we know that intuitively by increasing this, we'll get this will go up by increasing this. Now if you decrease this, you divide by a smaller number, and dividing by a smaller number gives you a larger number. Hang on, let me erase, select, freeform, delete. Right. So that's sort of how that works. Now, if we now we can actually go to discussing Le Chatelier's principle in action. Uh, if you add a certain species to a reactant, it'll shift to the side that essentially undoes it. So, like we said, if we add something to a system, it'll try and undo it. So if we add, say for example, if we add a specific reactant to the system, it'll shift towards the product side, because going to the product sides gets rid of the reactant. And the inverse is true. If you add some product to the system, it will favor the reverse reaction, since you will, it will favor the reverse reaction, since we have to want to try and undo that change, and the way we undo it is by adding, reactant. Another way you can think about it is that increasing the concentration by adding reactant, you increase the concentration of reactant, and therefore the forward rate becomes faster than the reverse rate, and then that will sort of play on until the system is at equilibrium again. And the inverse is true. If you add product, you increase the concentration of product, favoring the reverse reaction rate, and you will eventually get there. Right? Right. So consider this system here. If the system was initially at equilibrium and then some reactant was added, the system will no longer be at equilibrium. Which direction will it shift? According to Le Chatelier's principle, it should shift to the product side, since, if we add reactant here, the system wants to get rid of it, and the only way to get rid of it is by creating more product. And again, we can explain this with chemical kinetics. Q, if we can also do this mathematically. So at equilibrium, we have this here, 1 molar and 1 molar. If we add 0.5 molar of reactant here, we can calculate Q as 0.667, and since we're told that K is 1, which is smaller than Kc, we know that there must be a net shift from the reactant side to the product side, and therefore once it's back at equilibrium, 1.25 over 1.25 is 1. If you add an inert gas at equilibrium, nothing changes. For gaseous systems, some things that will invariably affect, for gaseous systems, if you increase the pressure, the system will try and decrease the pressure, and the way it does that is it shifts to the side with the least amount of gaseous moles, since we know from the ideal gas law that, oh whoops, let me go back here, P, oh shit, no, let me, since we know that PV equals nRT, we know that P is proportional to N, and we also know that P is inversely proportional to volume. And these will come very important later on when we discuss the logic behind these changes. Now, let me quickly erase that. Delete. Piece of shit. I hate this piece of shit sometimes. Bye bye. And then, alright. So now that that's done, if we increase the pressure, the system will try and decrease the pressure by shifting to the side with the least amount of moles, with the least amount of moles of gas, because we know that pressure is proportional to moles, which means that if we decrease the amount of moles of gas, we'll decrease the pressure of the system and go back to and it'll minimize the change. A similar sort of thing happens with the volume, is that a reduction in volume, since we know that pressure and volume are inversely proportional to each other, we know that if we decrease the volume, we will increase the pressure of the system, and therefore, since the system will try and decrease the amount of pressure being exerted, it'll shift to the side with the least amount of moles of gas to reduce the pressure and therefore account for the new volume. And then the inverse is true. If we increase the volume, there will be less pressure, and therefore it'll try and increase the pressure, and it'll go to the side with more moles of gas. So that's sort of the idea behind it there. The idea is that we're always trying to minimize the change or undo the change as much as we can. So sometimes, for some reactions, K won't change too much. Sometimes it'll change quite considerably. So here, for example, since there's 2 moles of gaseous product on the product side and only 1 mole on the reactant side, if we cut the volume by half, note here that since we cut the volume by half, the concentration doubles, and we can use Q to calculate that. And 2 squared over 2 is 2, which is greater than Kc. So the system must shift toward the reactant side, and therefore at equilibrium we'll have 2.25 over molar of reactant and 1.5 molar of product, which equals 1. However, in this case, the system is still at equilibrium and no shift is required because there's an equal amount of moles of gas on both sides, and therefore if you cut the volume in half, it won't change Kc, because there's an equal, since there's no side with less moles of gas, nothing's really going to change. Lastly, for exo-endothermic reactions, if a reaction is basically the idea here is that if you increase the temperature, while K does change, you can actually predict the change here. For an endothermic system, an increase in T will cause K to increase, and for exothermic ones, K will decrease. And again, the idea here is that since you add heat energy to the system will try and remove that excess heat energy. And for an exothermic system, the products have more potential, the reactants have more potential energy than the reactants. So by adding heat, you will favor the reactants, which have more potential energy, and forming that will essentially absorb the heat. And then the inverse is true, that if you decrease the temperature, okay, the system wants to try and undo the temperature change, and therefore it'll favor the product side, which is exothermic, and it will release energy to try and heat that system back up. And sort of, you can follow a similar line of logic for endothermic reactions. If you increase temperature, the system will try and it will favor the reactant side. It'll favor the reactant side, which are for an endothermic system, if you increase the amount of heat, it will try and absorb that heat by going to the side with more potential energy, which is the product side for an endothermic reaction, and the inverse is true. If you decrease it, it will try and release heat and go the exothermic reaction, which is reverse. Lastly, adding a catalyst to a system at equilibrium will do absolutely nothing. Yeah. So yeah, thank you very much.